All right, so here's what we're going to do today. We are going to expand our discussion of truth tables. Last time we ended on unknown evaluations, how to use a short sort of mini truth table that only had two sets of values. Today, we are going to run through longer truth tables to show you how, at least in principle, to do a problem of any complexity. All right, so first, how many rows does a truth table need? The technical formula for the proper number of rows is 2 to the nth. The exponent is the number of statement letters in the well-formed formulae you are examining. So if there's only one letter, one statement, you need two sets of values, one true, one false. If there are two statements, as there are on this sample, A and B, you will need 4 rows because you need to run through all the possible combinations, and there's only 4 combinations. But it gets geometrically more complicated. So when you get a third letter, A, B, and C, you then need 8 sets of values and 8 rows. If you have 4 constituent letters, you will need 16. So this gets complicated quickly, which is why I told you before why we need you to be operating at like 99 to 100% accuracy on calculating the values of the constituent statements. Because we're going to do ones where you have to do 32 statement values for one problem. And if you're getting 5% of them wrong, that means on every problem you will get 1 or more wrong. And that can throw off your final answer and cause you to get the entire problem wrong. Okay, so again, here's a sample truth table. We have, it is not the case of either A or not B. We set up the mechanics of this. Remember the innermost, you alternate between true and false. One step out, you do double false and double true. Those give you the 4 possible combinations where A and B are both false, where just B is true, or just A is true, and where both A and B are true. If you work this one out, the only one of the 4 situations in which the value of the statement is true is when A is false and B is true. Because in every other case, anytime that innermost or is true, the final negation outside the parentheses will switch it to false. So you need so to get the whole statement true, you need the A false and the B true, so that the or is false and the final negation switches it to true. All right, so far we have discussed 3 kinds of statements in this class. Most statements are contingent statements. Those are statements where the value of the complex statement will be true on some combinations of truth values of the constituent parts, and false on other sets of values of the constituent statements. Although there are statements that are always true, those are called tautologies. That's where the statement is true no matter what you do with the values of the constituent statements. So the tautology up there is P or not P. So when P is true, the left side of the or is true, and the statement's true. But when P is false, the right side of the or is true, and therefore the or is true. So P or not P is always true. That's called the tautology. In sort of the opposite, in contrast, we have the opposite possibility. Some statements are self-contradictory, statements that are false, no matter what the constituent truth values are. such as P and not P. Since it's an and, you both halves true. If the left half is true, if P is true, then not P will be false. But if P is false, then the right half is true, but the left half is not. In either set of values, the statement is false. The statement is always false, no matter what the constituent values are. So one possible use of truth tables is to determine whether a statement is contingent, tautological, or self-contradictory. All right. Now, let me look at 6.5 exercises. All right. Let me do, I'm going to do 2 of these for you. And then I'm going to start calling on you all to come up and attempt some of these. Because the key here is practice and repetition, like any good sort of math STEM style kind of learning. So let me look at problem 2, not P and Q. And let's run through the truth table for not P and Q. All right, so here's how we set it up. As we've said, you need to put the constituent letters over on the left side. You need to alternate truth values for the innermost, and then you need to double each truth value for the next layer. 2 to the n here, the n is 2, so you need 4 rows. So there's going to be 4 sets of possibilities. And you just need to be able to correctly identify the value of and rather quickly. So on the first one, where P and Q are both false, the Q is false, the P is false, which switches to true by the negation, but the and will still be false because the Q is false. So on the first set of values, when both are false, the and is false. On the second set of values, where Q is true, P starts off as false, but the negation switches it to true. You end up with true on both sides, and the value of the entire statement is true. On the third set, we have Q false. We have P starting as true, but it gets negated, so it switches to false. And you have both sides of the and as false. And then on the fourth valuation, where both P and Q are true, the Q is true, the P starts as true, but gets negated to false, and the and therefore is false. So that is the proper truth table for the statement, and it is a contingent statement. All right, so I think this is simple. How many of you got this? How many of you this was simple? You could do this, probably do it without all that much effort. Anyone have any questions about this? Because I want you to have this down, because this is the easy one. We're about to start doing 3-place ones, which are at least twice as difficult, and we're going to kick it up a notch, as I like to say, every class. Yes, ma'am. It doesn't really matter. What matters is that you do all the combinations. So as long as you know that you run it through all 4 possible combinations, it's fine. I think I always start with 0, 1, 0, 1. Honestly, I'm not self-reflective enough to know for sure, but I do know I always go through all possible combinations of it. So yeah. A lot of things like that. You know, there's certain forms that are more common or more accepted, but again, as long as you know how to use it and you can go through all 4 combinations, then we're good. Anything else? All right, let's do a harder one. Let's do number 3. P or Q and not R. P or Q and not R. All right, so here we have three letters, P, Q, and R. And therefore, how many rows are we going to have? We are going to have 8. Remember, it goes geometrically. So we're going to, again, I'm going to alternate for the innermost set of values, 0, 1, 0, 1, 0, 1, 0, 1. Then we'll double up, double zeros, double ones, double zeros, double ones. And then we'll do quadruples, quadruple zeros, quadruple ones. Again, if you get good at this, you know, it becomes second nature. It's just running through all the logical combinations like a computer, like binary. All right. So we always have to start with the innermost parenthesis here. So we have to start with everything is false. We're using the first set of values. So Q is false, R is false, gets switched to true. So we have an and that's false on one side and true on the other. So the and is false. So the right side of the or is false. The P also is false. So the or is false and the entirety of the statement is false. That's the first value. Second value, R is true. It gets negated to false. Q is false. The and is false on both sides, making it false, which means the right side of the or is false. The P is false. Therefore, on the second set of values, the or is false. Third set of values, the Q is true. The R is false. The negation switched the false R to true. The Q is true. The negated R turns out to be true. Both sides of the and are true. We have a true on the right side of the or. The P is still false, but it doesn't matter because the or only has to be true on one side for the statements to be true. Fourth set of values. The R is true, gets negated to false. The Q is true. The and turns out to be false because the right side is false. That gives us false on the right side of the P. The left side of the P is false. I'm sorry, the left side of the or is false because the P is false. Therefore, the statement is false. All right, now I'm going to do this next part a little bit lazy. Here's how I'm going to get a little bit lazy. And as you get a little more advanced on this, you will start spotting, frankly, easier / lazier, quicker ways to do things. This is an or, and that's going to be the final statement value, right? All 4 of the next sets of statements have P as true, right? So the next 4, the left side is always going to be true because the P is true, right? So that means this or is always going to be true no matter what's going on over here. Not if you see what I'm talking about. So I'm going to just do this. True, 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 true. Done. See how I did that? Again, the better you get at logic, the more things like that you spot. Because the final statement operator is this or. Anytime that left side's true, the or is going to be true no matter what goes on over here. And I'm going to save myself some time. Because if you don't learn to do stuff like that, this stuff's going to get a little tedious. But you've got to be 100% sure and understand how the operators work to do that. Because if you start doing shortcuts and doing it wrong, you're going to mess things the hell up. Questions, thoughts, observations? All right, well, let's do this. I want to see, I know I can do truth tables. I want to see some of you do truth tables. So this was 2 and 3. We skipped 1. I want to see you all. I want to volunteer to come on up and do 4. Who will do 4 for us? What brave soul. Thank you, sir. Come on up, do 4 for us. Who will do 5 for us? Yes, please come on up, do 5. Who will do 6 for us? You come on up, do 6. Great, thank you. I got to go around the back. I guess you just vault if you want. Your call, you should do that. Very good.
Do you have number 4?
What's
that I
that?
can look at?
Yes, I have a book. You may look right out of the book. Bottom left. Thank you. So 4, 5, and 6. And I'll even go get some wipes to sanitize between uses. Yes, thank you. All right. Oh, let's see how you did. All right. So here we have if and if P and Q, then Q. We've set up the truth table properly. We've got all 4 sets of values here. The first set of values, we have Q false. So we have, all right, let's actually start with the numbers. So we have P and Q, they're both false. The triple bar is true because the 2 sides match. So the left side of the arrow will be true. The right side will be false because Q is false. And that is the only one of the 4 combinations where the arrow will be false. Then on these other 3, P and Q don't match, which makes the triple bar false. Anytime the left side of an arrow is false, the arrow is true. So on the second set of values, it's true. On the third set, the P and Q don't match, makes the triple bar false, which makes the left side of the arrow false, which makes the arrow true. On the fourth set, P and Q match, the triple bar is true, Q is true, both sides of the arrow are true, therefore it's true. Well done, thank you. Yes. All right, now here we have number 4. If both P and not Q, then R. We have 8 sets of values set up. That's correctly set up. We should always look at the innermost parenthesis first. When P is false, well, actually on all 4 of these, P is going to be false on the first 4. That makes the and false because it needs both sides to be true. That makes the left side of the arrow statement false, which means on the first 4, that arrow's got to be true because you're always going to have a false on the left side of the arrow because the P is false. So those first 4 you can just rattle off as true all 4 times. The 5th valuation, we've got P true, we've got Q false, but gets negated over to true. That makes the and true, but the R is false. So they get this true on the left of the arrow, false on the right of the arrow. That is the one combination of the arrow that makes it false. We can look at the sixth. P is true. Q is false, gets negated true. The and is true. The R is also true, so we end up to have an arrow statement with true on both halves of the arrow. So it is true. The seventh valuation, P is true. Q starts off as true but gets negated to false, which makes this and false because the right half is false, which gives you a false on the left half of the arrow, and that makes the arrow true. And the same thing will happen on valuation 8. Because you have a true Q, it will get negated to false, which makes the and false since the not Q is false. And then you will have a false on the left side of the arrow, makes it true. Whew. Gets tired. But that's why we need to have these down rows 100%, because you need to be able to run through these quickly. All right, then we've got P, Q, and R. If either P or not Q, then R. Looks like we've got some variety this time. We start off with both P and Q as false. The negation on the Q makes that right side of the wedge true, which makes the or true. The R is false, so we have a left side that's true and a right side that's false, making the entire statement false. Second set of values. Again, the P and Q are both false. The Q gets negated to true, which makes the or true, so the left side of the arrow is true. But this time the R is also true, so it's true on both sides of the arrow, making it true. On the third set of values, the P is false. The Q starts off as true, gets negated to false. You get false on both sides of the or, which makes the left side of the arrow false, because both sides of the or are false, making the or false. And since the left side of the arrow is false, the statement must be true about the R. And that happens again on set of values 4. On set of values 5, we get P is true, which will make the or true, which makes the left side of the arrow true. R is false, however, so we get left side of the arrow true, right side is false, making the entire statement false. Sixth set of values, again, P is true, making the or true, which makes the left side of the arrow true. But this time the R is true rather than false, so you get true on both sides of the arrow, and the statement value is true. Seventh set of values, the P is true, makes the or true, which makes the left side of the arrow true. The R, however, is false, so it's true on the left, false on the right. That makes the arrow false. And then the last time, the P is true, making the or true. The R is also true, so we get true on both sides of the arrow, making it true. Whew. How are we doing? What do you think? You think y'all can do that? Any of the other exercises from 6.5 you want me to go over, or can I push forward and teach you something more complicated and more fun, more powerful? Infinite power. All right. So speak now or forever hold your peace. You're all solid on all of 6.5. Yes, sir. Yeah, is that the one with a P 3 times? Yeah, so that only has 2 values and you only do it twice. But yeah, that's kind of fun, a little different, but it's not all that difficult. Cool. All right, let's take it up a notch, because here is where we're going. The goal, so here's the primary thing we will use truth tables for. We are not so much interested in finding out the value of individual statements. What we are interested in primarily with the truth tables is to take entire arguments, put into logical, formological format, and then run through all the possible truth values of all the constituent statements in the entire argument, and then test to see if the argument is valid. So again, we're building on everything we've learned in the short term, but we're bringing validity back. And remember, an argument is valid if it is properly structured, such that if all the premises are true, then the conclusion must be true with 100% certitude. So what we're going to use the truth tables for is we're going to put not a single statement, but we're going to put the entire argument, two premises here and a conclusion, and we'll run through all possible values for the constituent letters of anything that appears in those statements to see if there are any combinations where all the premises are true, but the conclusion is false. And if there's even one situation where all the constituents, where all the premises are true, but the conclusion can still turn out to be false, then we have recognized that argument is invalid. And it only takes one set. So even if you're running through 32 combinations, it only takes one set of values where all the premises are true and the conclusion to be false for the argument to be invalid. Because it's kind of like saying, you know, it's a bucket, it's only got one hole in it. Well, one hole is one hole too many. All right, so here. This is the argument. If something is a dog, then it must be an animal. But this is not a dog, therefore it must not be an animal. So when I say it that way, it's kind of obviously not a good argument. Because obviously there are things that are not dogs, that are in fact animals. Duh. All right, so you'll see on that second set of values, when something is not a dog, but it is an animal, you will get both premise values as true. The conditional statement, the if D then A, will be true. The not D will be true, since the D starts off as false and then switches because of the negation. But the conclusion, not A, starts off as true, but it gets, the negation makes it false. So then you have that magic combination where both premises are true, but the conclusion, the predicted conclusion, is false, therefore proving the argument is invalid. See why that's important? See what we've proven there? So that's something we're going to use truth tables for a lot. All right. One more trick with truth tables. Now you see here we're quickly getting very complicated because now we don't just have one statement where we have to run 4 or 8 set of truth values. We have 3 statements. Now imagine we had 3 or 4 statements in the argument and we had 3 truth values requiring 8 sets of values. Now all of a sudden we're doing like 32 calculations for a single truth table. That's a lot of work. Let me let you know a personal secret. I'm actually quite a lazy person, but I'm lazy in a strategic way. I'm about to teach you how to be lazy in a strategic way. This is called the truth table shortcut. So here, remember, we are looking for the situation where there is a set of values, where there's a set of values here on the left side of the truth table that makes it such that both premises are true, but the conclusion is false. Anything else, we don't care about the details. So what this means is, if we find an argument that has a false premise, I'm going to be lazy, and I'm not going to calculate the rest. Why? Because it doesn't matter. Because as soon as I found one false premise, then it is impossible for that set of values to give us an argument or show that the argument has all true premises and a false conclusion. So here we've got if D then A, D therefore A. This of course is a valid truth table. The argument is roughly if something is a dog, it must be an animal. This is a dog, therefore it's an animal. So we're going to start on the first two sets of values. D is false. Well, anytime D is false, that second premise is going to automatically be false, right? So as soon as I do that, you've noticed I didn't put zeros or ones for the rest of the values for the rest of the statements in those arguments on that set of valuations. Why? Because they don't matter. Because anytime D is false and that second premise is false, no matter what happens in the rest of the argument, that argument will not give us an invalid set of values. So we're just going to exit out quickly and move on. Now for the third set of values, where D is true and A is false, I plugged true in for D, so I had to do a little more work, unfortunately. Hate doing work. But then I calculated if D then A, since the D is true and the A is false, the arrow statement is false. And as soon as I saw that, I then X out the remaining statement because I'm being lazy. Because I don't want to do more work than I have to. Why do more work than you have to? Then on the final set of values where both D is true and A is true, I plugged it in for D, so I've got a true premise, so okay, I have to do more work. I plugged in the values for both D and A, calculated the arrow statement was true, so that premise is true, so I had to still do more work. And then I saw that the A is also true, so the argument is valid. You see what I did there? You see why there are X's instead of zeros and ones everywhere? Now there's one other version of this trick. So anytime you have a false premise, the argument cannot be invalid. It's also the case anytime you have a true conclusion, the argument cannot be invalid. So in the same way, where you just immediately marked the values where premise D is false, where you just marked them off as things you didn't have to worry about, you could do the same thing anytime you recognize that the conclusion is true. So you could have just plugged in true on valuation 2 and 4, since A is true, put true down as the conclusion value and X'd out the rest of the work. Because when you get a true conclusion, no matter what happens with the premises, the argument's not going to be valid. So there you have it. Thoughts on this? Questions on this? All right, as usual, we're moving right along. Good. All right, let's do some exercises. And you know what? I'm going to skip the easiest ones. I'm going to start with 4, because 4 is the first one that uses 3 variables. If it rains and your tent leaks, then your down sleeping bag will get wet. If it rains and your tent leaks, then your down sleeping bag will get wet. Oh, I guess it wants an L instead of a T. Oh, all right, then we've got statement, your tent won't leak And the conclusion, your down sleeping bag won't get wet. All right, so those are our three statements. We have three constituent letters, R, L, and W. We will have 8 sets of values to run through. And this is the kind of situation that I was warning you about. So now we've got 8 sets of values. We've got 3 statements we have to test. That's 24 statements. That's like a lot of work. I don't want to do that. So usually the easiest ones to do are the single statement letters. And I'm going to start with this premise, not L. Anytime not L is false, we cannot have an invalid set of values. So I'm going to immediately plug in. So L is false on the first 2 valuations, which makes it true on those valuations. But it's true on the 3rd and 4th, which makes it false. And then true again on the 5th and 6th, and false on the 7th and 8th sets of values. So we already have 4 valuations where we have a false premise. So on sets of values 3 and 4 and 7 and 8, we've already eliminated those as sets of values we have to worry about. Now, as I said, anytime the conclusion is true is another situation where we don't have to calculate the rest of the statement values. So the conclusion is W is false. So anytime W is false, the negation is going to switch it to true, and we're not going to have to worry about the rest of those statement values. So on statement, on valuations 1, we don't have to worry because the conclusion is true. And on valuation 5, so now we're just left with valuation 2, set of values 2 and set of values 6. And we only have this, this complex statement to calculate. So now we got to do the real work here. All right, so on set of values 2, where R and L are false and W is true, R is false, L is false, that makes the and false. It makes the left side of the arrow statement false. That makes the arrow statement true. And we will also calculate number 6 set of values. R is true, L is false. Since half the and is false, the and is false. The left side of the arrow is false, making the arrow true. So what we have here on valuation 2 and valuation 6, what we have are 2 sets of values that demonstrate that the argument is invalid. Questions? So then you say, you write down invalid, and in truth, you only have to identify one of these sets of values that make it invalid. All right, did you all do 6.6A for the homework? I've only got 7 minutes. Are there any of the others from 6.6A that you would like to see me do? Yes, sir. Number 8. All right, number 8 says, it's an empirical fact that the basic physical constants are precisely in the narrow range of what is required for life to be possible. All right, so that is E for empirical fact. The best explanation for this fact is that the basic physical constants were caused by a great mind intending to produce life. B. If these two things are true, if E and B, setting up a then, if these two things are true, then it's reasonable to believe that the basic structures of the world were set up by a great mind, God, intending to produce life. R. Therefore, it's reasonable to believe that the basic structure of the world was set up by a great mind, God, intending to produce life. Therefore, R. All right, let's run through this quickly. So we have E, B, and R. That gives 8 possible sets of values. All right, so I will start with the first premise, E, and I'll plug in false on the first 4 sets of values, and true on the second 4 sets of values. And since I've got 4 cases where the premise is false, on those 4 cases, I cannot have an invalid argument. So I'm going to X out the rest of the work there on the top half of the chart. All right, I'm halfway done. I just did half of it. That was fun. All right, now I'm going to look at the second premise, B. And I'm going to plug in false, false, and true, true. Again, I have 2 more premises where we have 2 more sets of evaluations where we have a false premise, and therefore we cannot have an invalid set of values. All right, I look at this third premise. That looks like work. I don't want to do that. Not yet if I can avoid it. So I'm going to skip to the conclusion, plug in false and true for the value of R on 7 and 8. That rules out 8 as an invalid set of values. So then I only have to do the hard work, the complex statement on set of evaluation 7. E is true, B is true, that makes the and true, but R is false. So that makes true on the left, false on the right. This is not an invalid set of values because this third premise is false, and I've proven that the argument is structurally valid. Ta-da! Was the hard part just translating? Yeah. Because it seems like it gives you like a lot of stuff, and it's just E. All right. Well, look, we're going to do a lot more stuff like this in the days ahead. So if you're struggling with it, get this down cold, because you're going to need to do this. This will be on the exam. For next time, we'll do the truth assignment test. Thank you very much.